Week 12, problem 2. A laser beam is incident on two slits with a separation of 0.210 millimeters, and a screen is placed 5.25 meters from the slits. An interference pattern appears on the screen. If the angle from the center fringe to the first bright fringe to the side is 0.18 degrees, what is the wavelength of the laser light? Okay, so this is two slit interference. So pretty much the rest of these problems, for the most part, are going to be two slit interference and one slit interference, or diffraction, whatever. There's pretty much just a formula for these guys. I'm going to show you where it comes from, and that might help you conceptually understand it. And that way you'll kind of attune your spider senses, if you will. So if you're like, 85, 90% of this class, you can probably just punt the understanding and just go with the formulas, and you'll probably be well enough. If you are struggling and you're, trying to capture every point, maybe it'll help you out. Another good video for this is there's a video by Michael Van Biezen. I'll link in the comments below. Have a couple hours, watch his videos. It might help. He does a really good job explaining it. But I'll try and go through and get the idea. So for two slit interference, what this guy is, let's say I'm going to draw a picture. So we got, let's say, one slit there, one slit there, separated by a distance d, and there's a screen over here. So the idea here is, let's say you have, I'm going to use actual real line. Nope, there we go. So we have, let's say, a distance here. There we go. And this is in no way drawn to scale. So what's going to happen is we're going to have light coming through like this. So we have normal light. We're going to say it's coming on all planar-like. It gets to these points and acts like a point source. This is the diffraction. And it comes out like this. Oh, copy, paste up here. There we go. And then you're going to have interference between these two. Okay? So what's going to happen then is, let's draw a line here. We have, click, there. Why aren't you clicking? Drag, darn you. Yeah, whatever. So we have, when we have the equal distance between the two, they're going to amplify each other because they're going to be in the same phase. Because if you look at, since this is the same light and it travels the same distance to get to the center, it's going to, they're not going to be out of phase with each other. Well, if for some reason, let's say the light travels instead to this point up there, these guys might be out of phase a little bit. So I'm going to call this guy, R2 up here for the distance 2. This guy will be, let's say, R1. Well, if R1 in this case is going to travel farther, and let's say, for instance, you're not going to understand why I do this, but I'm still going to do this, and I'll explain it later. Let's say this distance right here happens to be lambda over 2. So that would say that R1, or the bottom, traveled 1/2 of wavelength farther than R2. So what that does then is it means that they're going to be now out of phase. That's going to cause destructive interference. So I'm going to make let's do it this way. There we go. Go to this. So this is going to be representing amplitude. So here we have exactly 1/2 wavelength difference in the lengths. We're going to have destructive interference, i.e. dark spot, no light. Okay, so with that said, we now need to find some sort of way of formulating this. So the way this is done, or one of the ways of doing it, is we want to find out how much longer this actually is. So here we're going to have a distance. We're going to call this big D, the distance. We're going to have another distance. We're going to call this y. This will be the distance from the center. Actually, there we go. I'm going to call it from here to the center. This distance y from the center. Now this is not drawn to scale because this right here, d, is like 5.25 meters, and this guy is like 0.21 millimeters. That's like 1,000 difference, 10,000 difference. It's a big difference. So this is not drawn to scale. So first thing we want to do is we want to find how far further R1 actually traveled than R2. And the way we're going to do that is we're going to swing this down in an arc like this. So we just took that and we just, like a door hinge, blink, swung it down, and we're going to look at how much this distance is here. So this is the small angle approximation. The small angle approximation is every now and then in life, you've probably seen it a few times already, where they say sine of theta equals theta. Kind of, sort of. Well, that's the small angle approximation. And the way it's justified is, let me draw a circle here, go supersize, get a shape, draw a circle, bam. Yes, there's good. And then, nope, you can go away. We're going to draw a line. So what it's saying is, I'm going to say this is the center. And let's do it this way. So we have the center, let's say about here, goes there. And we have another. So we're going to say this is a small angle. And from here, we're going to, I can make a smaller angle. By small angle, they usually mean like, I don't know, 1/10 of a radian type thing. All right, so this is a small angle. That's like what, maybe 3 degrees? So, nope, straight up and down. There you go. Let's do it there. A little bit over, and I'll make the circle blue just to highlight what I'm talking about. Color blue. All right, so we go in, zoom in really far, and what the small angle approximation is saying is the arc length right here, if you measure it in radians, is just going to be the angle, theta, times r. So that's radians. So that's the length of the circle, the arc length, is going to be the radius times the angle. Well, the length of this line, which is straight up and down, is basically sine of theta times the radius times r. So for a small angle, you can look at this and you're like, yeah, this arc right here, when you look at it really close, is really pretty much just like a straight line. That's why when you stand on the earth and you look around, you're like, oh, this is pretty flat. It seems reasonable that the earth would be flat, because when you're so small and the earth is so big, it pretty much might as well be flat. And that's the same idea with the small angle approximation. Small angle approximation is just saying for a small angle, this arc length right here is pretty much sine theta. And that's where this small angle approximation, where did it go? Up here comes from. You'll also see tangent of theta is kind of sort of sine theta, which is kind of sort of theta. Well, tangent of theta is just sine theta, cosine theta. And when you get a small angle, it's close to 0, which means that cosine theta, this guy, is kind of sort of 1. So what you're really getting is sine of theta over 1, which then is basically kind of sort of theta. You don't have to do this using the small angle approximation. You can actually calculate everything out and be exact. But for this class, small angle approximation is what they expect you to use, and it's close enough. So we're going to go with that. All right. So back from my tangent, which is approximately sine theta. Never mind. It's a terrible, terrible joke. All right. So this guy right here, we got to find this length right here, and this right here is the arc length. Well, we're going to say it's pretty much sine theta here. So what we want to find then, this guy here is a perpendicular. So we now have a triangle. It's kind of hard to tell because I have done a terrible job drawing at this point. But here, I get that too. Oh, there we go. This is a right triangle right here. So we know what this side is. This side is going to be D. And we're pretty much kind of given what this guy is here. We're going to, I'm going to call that guy theta. And the way we're going to find out what theta is we're going to draw a line like this, straight across. And we're going to look at another angle. So we're going to look at, you can stay there, this angle right here. And that's going to be the same theta. To prove that, do a little bit of geometry real quick. So this guy here, 90 degrees. So this guy here is going to be 90 minus theta. Because one angle plus the other angle plus 90 has to equal 180. Well then, this angle right here is also 90. I know it's not the way that I drew it, but kind of sort of supposed to be. And part of this assumption is that these two lines right here that totally aren't parallel, I'm approximating as parallel. And they can be approximated as parallel because this is not drawn to scale anyway. This D is supposed to be huge, and this D is supposed to be small. So if you're like, wow, your angles don't quite match up, it's true, they don't quite match up, but they kind of sort of almost match up, and then be far better at matching up if I actually drew it to scale. All right, so this guy is 90 minus theta, and this guy right here is 90 degrees. Then this angle right here would be 90 minus quantity 90 minus theta, which in the end is theta. So I would recommend, if you get time, people are busy in life, and if you're, it might actually help you to draw this picture out, look at it a few times, and actually be able to do this. It'll give you a better understanding of what's going on. All right, so now we have two triangles that we're kind of working with here. We're working with this triangle, and we're working with this triangle. And this triangle right here, we know is going to be, let's say, lambda over 2. I'm going to say lambda over, no, I'm going to say lambda. Before I say lambda over 2, I'm going to say lambda, because what I'm looking for, I'm not going to look for a dark spot. I'm actually going to look for a bright spot. We could do it with lambda over 2 first as well, but we're going to start here with doing it this way. For two slit interference, it's usually easier to find bright spots. So to make it a bright spot, it's going to be lambda. All right. So we write this out. We're going to say here sine of theta, which is about theta, equals, now say sine of theta is opposite over hypotenuse, SOHCAHTOA. So opposite in this case would be lambda, so opposite over hypotenuse, which is the small d, which equals, and we have another sine of theta over here, which is again going to be opposite over hypotenuse, where the opposite will be y, and the hypotenuse, now the hypotenuse is actually going to be y squared plus big D squared square rooted. Well, this y is really, really small compared to the d. So this is pretty much going to be d. And that's another approximation we're going to use here. So what we're going to have then is for the first bright spot, we're going to get, I'm going to throw in an m there, I'll explain it in a second. We're going to have m, let's see, lambda big D over small d. Now m just means it's just an integer. It's any number of lambdas. And so what's going to happen is you're going to get constructive interference. You have any number of lambdas here. Any number of wavelengths. If you have complete wavelengths and they match up, then you're going to get positive interference, constructive interference. And that's what that m means, is any integer value of. Right. So this is the formula you're going to use for two-slit interference. And what's more, and this is going to give you bright spots, i.e. constructive interference. And on a quick tangent in life, the other formula they're going to use is going to be m lambda d over a. And this is going to be single slit interference or diffraction. Both single and double slits have diffraction and interference. I'm going to call it single slit interference though. It doesn't matter. The big part is the double slit or the single slit. And this will find you minimums for dark spots. The way I keep these two straight is when I see the A, I think of aperture, like a camera. Since a single slit is just like a single hole, it's basically the aperture size. As far as I know, that might actually be what A actually stands for. And the way I kind of visualize it is you take this D, you just hit the head a little bit, curl it over, and bam, the D turns into an A. So this is for two slits, and it gives you bright spots. This is for a single slit, and it gives you dark spots. Okay? All right, so now that I've done all this background, let me actually get to the problem I was trying to solve the first time. All right, so a laser beam always feels like there should be a Z in there. And two sides with a separation of 2.10. All right, so I'm going to draw the picture for reals this time. So we have up, 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 and I'll draw it way over here. So this is 0.21 times 10 to the negative third meters. And this guy right here is 5.25 meters. Okay? Got that? An interference pattern on the screen, if the angle from the center fringe, from the center fringe to the first bright fringe is 0.8. Okay. So now I'm going to draw the interference pattern. So the interference pattern is strong in the middle because we get positive interference. And then we're going to have a minimum and then another maximum. And then I can do the same on this side, but I don't care. And it's saying that this angle right here is 0.180 degrees. Okay? So I'm going to use trigonometry. I'm going to start by saying that sine of theta, which is pretty much theta, which equals y opposite over hypotenuse. So the opposite here is going to be this guy. So I'm going to say y. And the hypotenuse is going to be this guy. But since it's really far away, I'm going to say that the hypotenuse and the the hypotenuse and the adjacent leg are pretty much kind of sort of the same. So I'm going to call it d at a distance 5.25. In reality, this might be like 5.24, a few nines, and then the answer. But I'm going to say it's basically this. Okay? Then I go back to my formula. I'm like, all right, we have a y here, a d there, and we know it's the first fringe, so the m is going to be 1 because it's the first. Lambda, do we give lambda? They better give us wavelength. Sure, I hope they give us wavelength. Otherwise, I'll be completely lost. Oh, no, looks like pretty much lost. Laser beam, screen, interference pattern, center fringe. What is the wavelength? Oh, we're looking for the wavelength. Okay. Times lambda over, and then we're not going to use A for aperture, we're going to use the D for distance between the two. So I'm going to rewrite that as 2.1 times 10 to the negative fourth, because that's this guy's D. And then this guy is theta, which is going to be 0.180 degrees. Now the problem is we need to be using radians, so we need to convert the degrees into radians. So the way I do that, which is pretty much the way everyone does it, is you can pick any point on the circle and just match up the radians and the degrees. So what I remember is pi radians is 180 degrees. You can also use 2 pi and 360 or 90 and pi over 2, whatever makes you feel good in life. All right, so I'm going to call this 180 times 10 to the negative third. 1, 2, 3, right. So then the 180s cancel, and we have pi times 10 to the negative third. Okay? Now I know this is terribly sloppy, but you'll get over it. So rearranging this, we have lambda equals 2.1 times 10 to the negative fourth divided by so move this guy up here. Oh, no, we need to multiply, not divide. Multiplied by pi times 10 to the negative third, which gives us 3.6, I'll wolfram this. 2.1 times pi. I know it's going to be like 6.3. Nope, 6.6. All right, so we have 6.6 times 10 to the negative 7th, which equals 660 times 10 to the negative 9th. All right. So they probably want it in nanometers, I'm guessing. So 660. There we go. All right. So to backtrack briefly, the formula that we used for this problem, and we're pretty much going to use for every problem, is this guy right here. This is double slit interference. This is single slit interference. Double slit gives you bright spots, and this formula for single slit will give you the dark spots, i.e. the minimums. And we'll work out how to find, convert one to the other more or less later. Not hard. Basically, the dark spots are halfway between the bright spots. So it's worth, if you can, understand where the formula comes from, because that way, when you get down to a problem you have no idea what to do, you can kind of conceptualize your way through it. And it might get you an extra point or two actually understanding it. And below I have links to some other videos which are pretty useful. If you have time, an hour or two, watch them. If not, I understand. My feelings will not be hurt. So use the formula, got our answer, sine of theta equals theta, small angle approximation. Make sure you use radians, and bam, get the answer of 660 nanometers, which seems pretty reasonable for a laser beam. Maybe, I don't know. So, hope that helps you. If this helps you out, hit like, subscribe to my channel. If I do something wrong, leave comments. Helps out the team. All right? See you on problem 3.